Okay. So good morning, everyone. Welcome to the colloquium of the Physics Institute. Today we have the pleasure to have with us Professor Martin Kuss from Geneva that will talk about cosmology. And I will ask my colleague Mauricio Galvão to introduce him.
Sorry, everybody hears me. It's a great pleasure to introduce Professor Martin Kuss. He's from the University of Geneva, which hosts the Department of Theoretical Physics and a group of leading experts in cosmology and general relativity. And I first met him personally in one of his 3 times he came here to Brazil. And after an event in National Observatory, we went to a barbecue house called Majorica. And we were together with his nice wife, Apple, and also Professor Yoav Varga. And I hope you enjoyed as much as I did the gorgeous meal there. He's an associate professor there at the University of Geneva, and professionally he has more than 100 papers, and he will talk today about these 2 satellite missions in which he is involved, and he has been working both of them. In fact, one of them, the Planck collaboration, is already over, but he has been involved for more than 10 years in both of them. And they were developed simultaneously. Planck is already over, as I told you. But Euclid, the second one, which he will be talking to us about, is still in progress and is scheduled to be launched, I guess, around 2020. And Planck, the one which is already over, he was a member of the core team. And Planck received several awards. Perhaps the most prestigious one is the 2018 Gruber Foundation Prize, which is perhaps badly comparing a kind of sort of Nobel Prize for cosmology, and sometimes several of their recipients have in fact been delivered Nobel Prize afterwards. And Euclid, he is a co-coordinator of the Theory Science Working Group. And without much further ado, I guess we should pass center stage to Professor Martin Kuss. Thank you.
Thank you very much for this, firstly, for the kind invitation to give the colloquium, which is really a pleasure, and for the equally kind introduction. Let me try to switch to my screen sharing. There we go. I hope you can see my screen. So it is indeed a shame that I can't actually be in Rio de Janeiro like right now. It was indeed a huge pleasure every time I was there. And because now here it's early winter, so usually the weather is not so good. It would be really much nicer to be in Brazil. So I'm going to talk indeed about 2 satellite missions, Euclid and Planck. I will give a bit more space, I think, to Planck because there we actually have data, while in Euclid at the moment it's no longer just a paper mission. I actually found some photographs, but it hasn't yet been launched. And so just to say, so the picture, so the background here, the sky is actually a Planck reconstruction of the magnetic field of the galaxy. But I will be mostly speaking about cosmology, and now it would be actually useful if I could switch screen. Great. So that's just a brief outline. I'm a bit afraid that I prepared much too much. We will see. You can just turn off my connection if I go on for too long. And so I will start a bit talk a bit about Planck, the satellite, and what it observed, which is the cosmic microwave background. And then I will say a few words about what we think we know about cosmology, which is always a bit strange because on the one hand, we think we know a lot. On the other hand, it has mostly taught us all the things that we don't actually know. And then I will talk a bit about Euclid, which is the next European cosmology mission. So here a very brief introduction into cosmology. Cosmology is probably one of the oldest, well, science, one of the topics that mankind has always wondered about. So what's out there? How did it all start? But it's also one of the most modern sciences because it's barely 100 years that we actually have a theory that can describe the universe. So with Einstein's theory of general relativity. And then the data, I mean, even in the 1920s, the scientists didn't know whether there was more than one galaxy. And so observations, they are really all quite recent, and we are rapidly learning new things. And so in that sense, it's one of the oldest, but also one of the most modern sciences. Okay. And for Planck, particularly a key object is the cosmic microwave background. And this was predicted already earlier in the 40s and 50s by Russians and by Americans, but it was by chance discovered by two engineers, Penzias and Wilson, in 1965, and they tried to build a very, very good antenna, and they just couldn't get rid of a noise in their antenna. And after looking for a while, someone told them they could call up the Princeton physics department, and so they talked to Dickey, and actually the group around Dickey was just then about to build an experiment to measure this radiation, and so famously Dickey came off the phone and said, "Boys, we have been scooped." And so in the end, they wrote two papers, one by Penzias and Wilson about the discovery, and one by Dickey et al. About the interpretation, and the Nobel Prize went to Penzias and Wilson. And so the Princeton physics group initially didn't get any Nobel Prize. In the end, actually, last year, Peebles, who was part of the theorist in this group, got the Nobel Prize that was linked to this discovery. And there is actually a third Nobel Prize that was given to COBE, or actually a double, because both Nobel Prizes in 2000, two of Nobel Prizes of 2006 went to the COBE team. The COBE was the first satellite to reliably measure the cosmic microwave background. And this is in some sense really amazing. Actually, I once asked Peebles many years ago whether he was disappointed that they hadn't gotten the Nobel Prize. And he said, not really, because it was such an exciting time. And so here I like to think a bit of Indiana Jones going into the Temple of Doom and finding some ancient relic, because they realized that this noise that they were observing, this noise was actually were microwaves that had traveled all the way across the universe, and that originated from a time when the universe was 1,000 times smaller. And so this was a really an amazing discovery. You know, I mean, even compared to Indiana Jones, I think I can say this is one of the most amazing things you can actually see. And so what is this cosmic microwave background? So let me take a quick look back in time in cosmology. So looking around us, we can see, and so this shows this figure from the Hubble Key project. As we look further away, we can see that objects, as they are further away, they move more quickly away from us. So as distance increases, recession velocity increases. And so everything around us moves away from us. But the idea is not that we live in the center of the universe, but instead that the universe itself is expanding. And so that's why everything moves away from every point. So you can try it by taking a balloon, and if you inflate the balloon and you put some points, you can see that all the points move away from all the other points. Okay, but if the universe is expanding now, well, then it was smaller in the past. And so if you go now into the past, the universe gets smaller and things get closer together, so the universe gets denser. And if the universe gets denser, then it also gets hotter. That's basically the Stefan Boltzmann law. And as the universe heats up, at some point, the atoms will become ionized. Okay, and so there is a period when the atoms are not ionized, the universe is, so this happens at about 3000 Kelvin. And so as we are below 3000 Kelvin, the universe is neutral. And as we go above 3000 Kelvin, the universe, the universe is ionized. And so we have lots of free electrons, but free electrons are very good at scattering light. And so effectively the universe becomes opaque at this point. And so running the movie forward again, the light here is scattered. This is like a fog. Then as the universe now cools, it becomes neutral. And so the fog lifts and light can travel all the way to us. Okay, and because the size of the universe increased by a factor of 1,000, the radiation now is not a black body with a temperature of 3000, but with a temperature of about 3 degrees Kelvin. Okay, and so if we take a picture, then we literally take a picture of this wall of fog that is as nearly as far away as it can be, because it's nearly at the beginning of the universe. So the age of the universe at that time was about 380,000 years versus 13.8 billion years today. And so what do we see when we do take a picture? So this is from the COBE satellite. So these are the first pictures of the cosmic microwave background. And the first thing you see is that the universe is very homogeneous. So the temperature of the cosmic microwave background is the same in every direction. So this is very important for the cosmological principle that we don't live in a special place. Then when you zoom in, then we find at the level of a few millikelvin that there is a dipole. And so the idea is that this dipole is our motion with respect to the rest frame of the universe. Okay, and then when we zoom in even more, then we start to see on the one hand this band, and on the other hand these fluctuations here. So the band that is our galaxy, the Milky Way, and these fluctuations, these are the seeds from which all the structure in the universe formed. Okay, good. And so to observe this cosmic microwave background, you need a microwave telescope, because today the microwave background is at about 3 Kelvin or 2.7 Kelvin, and this is in the microwave range of the electromagnetic spectrum. And so you can see that we are somewhere at the 100 gigahertz frequency range and at the centimeter level wavelengths. And you can also see, does it penetrate Earth's atmosphere? Here it says, no, that's a bit too pessimistic. We can measure the cosmic microwave background from the ground, but it is much easier to do it from space. And so going to space is really something that helped. Originally, there were attempts to measure the cosmic microwave background before COBE, but they had a really hard time getting any good results. So effectively, they didn't manage. So now, before going to the Planck results, I should mention that Planck, like all satellites mission, is a very large collaboration, and we are just some tiny wheel down here in the big group. So here is a photograph of Planck before launch. So Planck is about a 4 by 4 meter or 4 meter cubed object. This is actually a bit similar for Euclid. It's about 2 tons mass. That is actually also going to be similar to Euclid. Maybe, yeah, it has about 1 kilowatt of power. It contained 2 instruments, the low frequency instrument and the high frequency instrument. And the low frequency instrument operated at 20 Kelvin. You can cool passively to about 20 Kelvin with the help of these cooling grooves. to go to 100 millikelvin, which is the HFI temperature, you need active cooling. And that's why Planck had helium on board that was used to cool the high frequency instrument. And when Planck ran out of the coolant, then the high frequency instrument stopped working. And we will see that in a moment. Okay. And yes, so when you look into Planck, so Planck is literally a microwave telescope. Here is a mirror. So this is about 1.5 meter effective size mirror. And inside you can see the Planck focal plane with the pixels. Now these days, modern experiments, they literally have like a CCD that measures microwaves, but Planck was designed, we will see, in the 90s, and so it is a bit more basic in its design. So Planck has some order of 70 pixels, so it's not exactly a megapixel camera like your phone. And here you can see the different pixels, and you can also see the frequencies. These are the different frequency channels. Nonetheless, this is one of the big advantages that Planck has, that it has so many frequency channels, because that helps finding out what you're actually seeing through the frequency dependence. And you can also look at the angular resolution. So you see that the best channels, they are between 5 and 10 arc-minute angular resolution. So space telescopes like Hubble and in the future Euclid, they are typically at the point 1 to 0.2 arc-second scale resolution. So this is a much lower resolution. Okay. And okay, the box here is mostly to show the sensitivity, which probably doesn't tell you much. But the point is that the actual measured sensitivity of Planck is perfectly in line with what the goal was that was the goal to achieve. So Planck did actually better than expected. Okay, and so here is a brief timeline. So you can see that it actually all started just about at the time of COBE. For those who know about COBE, the COBE satellite. So 93, the proposals came in, and then it took from 93 to 2009 until Planck was actually launched. So we used to make jokes about how long it took. So I actually joined Planck only somewhere around here, not so much before launch. So this was a good timing. But I realized that I joined Euclid even a bit earlier than Planck. So I joined Euclid in about 2006, when it was not yet called Euclid. You note that also Planck wasn't called Planck in the beginning. And so 2006 until 2022 is actually also 16 years. And so effectively Euclid will have the same hugely long development that as Planck. So this is just a feature of space missions. Yeah, particularly of European space missions, because the Europeans are significantly slower than, for example, the Americans. So in between COBE and Planck, there was another satellite called WMAP, and the WMAP proposal was submitted after the COBRAS and SAMBA proposal for Planck. And so the Americans were significantly faster than we were. Okay, so then Planck launched in 2009. The nominal mission is not so important. That was what it had to do. But then in 2012, it ran out of cooling. And so then the more sensitive high frequency instrument was turned off. And then in 2013, it was ejected from its orbit and placed in some Earth trailing orbit, actually here more precisely. And then it was turned off also late in 2013. So it ran basically from 2009 until 2013. That was the satellite. But then the data release is the first data release about the nominal mission was in 2013. So when actually the satellite was turned off. And then the first analysis of the full data was in 2015. And the legacy analysis, those papers went on the archive in 2018, and they were published just this September. So you can see that the final deeds of Planck, the final papers published, that happened just 2 months ago, after 2 decades of hard work. So you can see the kind of the timeline that these missions take. And so here is just a nice picture from launch. Planck went not in a direct Earth orbit, but it went to the second Lagrange point. That's the point where the centrifugal force from its orbit is balanced by the attraction of the Earth and the Sun. And the big advantage is that it has the Earth and the Sun in the back. And there it just turns and scans the sky. And it just goes around and around, so around the Sun together with the Earth. And so every half a year, it makes a complete sky map just by scanning around and round. Okay, and when you have this complete sky map, you can open it up and project it into this kind of sky map. And so every year it made 2 sky maps. Okay, and then you can see some things. Okay, so however, since, as you can see, Planck is scanning round and round, its basic data product is not directly a sky map. It's really this time-ordered data that comes from the scanning. And so here you can see what Planck really sees. And so this is 2 different frequencies. And this is a channel that this is a sensor that doesn't look at the sky. This is for calibration. It just looks at nothing at all. So there should be no signal here. And in the 143 gigahertz, you can see these oscillations. This is the dipole that we saw earlier. And then these blimps here, these are the galaxy crossing. At the higher frequency, the dipole is much less important and the galaxy crossing is much bigger. Most of the galaxy is just much higher and dominates this signal. And then you see all of these lines, these are cosmic rays. As it turned out, Planck had just launched during a period of extremely high cosmic ray activity, and it took a lot of work getting rid of all of these cosmic ray hits. Okay, so cleaning, this was actually one of the things I was also playing a bit around with. Okay, so just to say, if you have any question, if anything is not clear, please don't hesitate to ask. Okay, so once this time-ordered data is cleaned, then you project it back on the sky. Then you can make noise maps based on the sensitivity of the detector and for how long you integrated things. You know what the sensitivity is. You see it's inhomogeneous, the noise. This makes the analysis more interesting. So these are lots of fun statistical problems. Okay, and so then you project it back on the sky, and this you can do for every frequency. And so in some sense, then this is what Planck really sees. So these are the different Planck frequencies projected back on the sky. And you see also the wavelengths are between 1 millimeter and 1 centimeter, roughly, or half, like a third of a millimeter and 1 centimeter. And you can also see that the foreground, that what we really are interested in cosmology are these seeds that form the structure. So how do these look like? And the galaxy and the foregrounds, they vary as a function of frequency, and especially at the high frequencies, they totally dominate. And so what you then do is you take all of these maps, you put them into a magic machine, you turn the crank, and out come your different components. Okay, so there were actually about 6 different such methods that try to take all of the frequency maps and combine them in various ways. So you use things like independent component analysis or Bayesian model fitting and similar methods to split them into the different components. So here is the cosmic microwave background. So really the picture of the universe that we are interested in. And here is synchrotron radiation. Here is free radiation. These are dust. And then there are also different molecular lines. And these are all very interesting for the astrophysicists. But for the cosmologists, those effectively go into the recycling bin. And we really want to concentrate on this plot. So this is the plot that we want. So ESA was always a bit disappointed with Planck because Planck was launched together with another satellite called Herschel, and Herschel just made a lot more beautiful pictures than Planck that were a lot better for PR. It's because this picture here actually takes some explaining, right? So for us, this is nearly the face of God. So this is a photograph of the universe when it was 1,000 times smaller, which is totally amazing. But in terms of beauty, possibly it leaves a bit to be desired. Effectively, we think this is effectively an isotropic Gaussian random field. Okay, it's maybe not the most Gaussian random fields, or maybe not the most exciting pictures you can make. So in general, we don't use this for our analysis. Instead, we are interested in a statistical analysis. And since it is effectively an isotropic Gaussian random field, if you have a Gaussian random variable that is zero mean, because here the average temperature we subtract, then this Gaussian is characterized by its variance. Now, when you have a whole field, it's actually the power spectrum or the 2-point function that is relevant. Now, a slight complication is that we are on the sky sphere, and so when we want to calculate the 2-point function in Fourier space, we don't just do the flat Fourier modes, we do it on the spheres, so we decompose it in spherical harmonics. And then what we are interested in, so these are the expansion coefficients, so we want the 2-point function, and the orientation, which is encoded in the M, is not relevant. The only thing that is relevant is the scale information, so we want this CL. And so this L here is like the modulus of K in Fourier space. So small l are large scales and large L are small scales. And so what you see here is the signal, and you see this is the noise. The noise takes over on small scales, and on large scales, we are signal dominated, but the larger the scale, the less Fourier modes we have, and therefore there is a larger statistical uncertainty here. Around here, you get the optimally small error bars, and then it increases because of the noise. And so this is the binned power spectrum, okay? And so the dots is the binned power spectrum. Up to here, Planck is signal dominated, and the blue curve is a model curve. And I should say that neither that the plot looks so nice, nor that the model curve goes through it is very obvious. So this is a picture from my PhD thesis. And here you see the data about 1998, and you cannot even see the first peak. There is just a bigger variance. And this was my favorite model in 1998, and you can see it's basically just flat. And you can see that this model, just flat, is ruled out at a very, very high significance today. So it is really not automatic that we have a curve that goes through all of these points. Okay, and here is another nice plot, now in log scale, where you can see really how many of these peaks we can now actually observe. So in 98, we didn't even have the first peak. Now you can count 1, 2, 3, 4, 5, 6, 7. Okay, then. And also it's, so to get to here, we took our time ordered data, which was about 10 to the 12 samples. It was compressed into maps that were of the order of 10 to the 7 pixels. Those were compressed into power spectra, which is of the order of 10 to the 4 numbers. And then in the end, this curve that goes through it is described by 6 parameters. And so so this is a gigantic compression. So all of this, particularly this Gaussian random field, can apparently be described by 6 numbers. So this is really a surprise how simple the universe appears to be at its very core. And why this is, we are not sure. Now Planck also measured other things. So this is just a very quick point. It measures polarization. So here is cross and auto spectrum in polarization. The model fits also here. And I mean, I could, of course, give a whole talk about this, particularly about the polarization I don't show here, about the so-called B rotational polarization modes. But the photons, when they come to us from this last scattering surface, they're also deflected by gravitational potentials. So they also undergo gravitational lensing, and Planck can also extract this lensing, and that tells us something about the amount of structure between this last scattering surface and us. So there is really a lot of information in this CMB. But what do we actually learn from it? So what do we see here? So effectively what we see here is a processed initial spectrum. So we think that some initial process that we call inflation sets up fluctuations on all scales. And so then there is a largest fluctuation that has just the time to collapse gravitationally. Okay, and so at the time when last scatterings emits the CMB, there is this scale that has just collapsed. This is this first peak. And then there is a smaller scale that had the time to collapse and expand, so an underdensity, but because we're quadratic, this also gives us a peak, then collapse, expand, collapse, the next peak, and so on. So that gives us this peak sequence. Okay, and particularly the first peak, or generally the frequency gives us a known ruler. And if we have a known ruler, we can effectively measure the distance to last scattering. So we have a distance between us and the universe when it was 1,000 times smaller. And a second thing is that when we have these oscillations, for pure radiation, it turns out that the expansion and the compression peaks, that they have the same size. But we don't just have radiation, we also have matter. And so the matter that is dragged along by the photons, this is the normal matter that we call baryons. So in a compression peak, it actually helps, the matter actually helps to compress. And so the compression peaks become deeper, and the expansion peak, the gravitational attraction of the matter resists the expansion. And so the expansion peaks become shallower and the compression peaks become deeper. And so we can use these peaks also to measure how much normal matter we actually have. And then there are also many other things, like what's the initial spectrum that goes through here, and so on. Okay. And so here is an illustration from the webpage of Wayne Wu that shows a bit that as we vary the cosmological parameters, how does this model curve change? You see here how the peak height changes, and how in the yellow curve, how the peak location changes. And then you just crank this through a machine and you look at all the constraints that come out. And what comes out is this. Okay, so this shows that the world is flat. There was actually a newspaper that at some point titled that. So specifically, the universe is spatially flat. And you can see here, this is the amount of matter, and this is the amount of what we call dark energy that makes the universe expand faster, the cosmological constant. So you can ask me later for more details about that. And you can see that using the Planck data, we actually shrink into this blue contour. And when we use also galaxy surveys in addition, then we shrink to this very, very small contour here. And so the universe is flat up to 0.004 in relative density at 95%. So the universe is extremely flat, and we have about 30% matter and about 70% cosmological constant. And then through the peaks, we also know that only about 5% of the matter is normal matter, and the other 25% is some other kind of matter that we call dark matter. So the CMB effectively tells us that only 5% of the stuff in the universe is the kind of things we observe here on Earth. And the other 95% are something else. And this is one of the big puzzles, and one of the reasons for future satellites like Euclid is to try to understand what are these 95%? What are they really made out of? Okay, and then we can also determine the age of the universe. So the age of the universe is 13.8 billion years plus or minus 20 million years. So we think we know the age of the universe up to 20 million years. That's a lot less than the length of the age of the dinosaurs. Of course, one important point is that this always depends on the model. So in cosmology, you always have to interpret your data within a model. And then where exactly you are on this line also depends on the current expansion rate of the universe. And you can actually look at the color scale here and compare it to there. And here we are at the upper end. So we are somewhere here. And so we measure the current expansion rate to be about 68 kilometers per second for object at the distance of 1 megaparsec. Okay, and then here I really would need to talk another hour. So as I said, we think that something created all of us, so the galaxies, the sun, the earth, us, we are really the product of quantum fluctuations in the early universe. And so here what you can see is that so this is the slope of the spectrum of these fluctuations as a function of scale. And so it's not exactly one. One would be just by definition a scale invariant spectrum. And so the fact that we are not at one means that we see some dynamics in the early universe. And the second point is that there are strong constraints on the amount of primordial gravitational waves, because whatever created initial fluctuations should also have created gravitational waves. And this puts strong limits on different models of the early universe. Okay, now here are some constraints on the nature of this dark energy component that probably will determine what happens in the future. So if it is a cosmological constant, the universe will just expand faster and faster forever and will become colder and colder. And so the data just shows here is a constraint on the pressure. The cosmological constant has -1 and the data is consistent. And here are tests if we see either a modification of general relativity or an additional clustering component that we don't know what it is. And you see that we actually observe neither. And it is particularly these two plots are the main scientific aims, or among the main scientific aims of Euclid. So because you see here the error bars are of order 1. So Euclid should shrink these error bars by at least an order of magnitude, and actually also here. Okay, but you can also do particle physics. So here are constraints on the absolute neutrino mass. Particle physics gives us amazing constraints on the differences of the neutrino masses, but it's hard to measure the absolute neutrino mass scale. But the neutrino mass changes the way matter clusters, and so we can also put constraints on this. And so here you can see that at the moment it's about 0.12 electron volt. The minimal mass scenario is at about 0.06, so we are not far away from a guaranteed detection. And again, the next generation of surveys hopefully will be able to detect the absolute neutrino mass case. And here,
short question.
Yes?
If you please, Martin. In the previous figure, which model of modified gravity you were dealing with?
So this is the phenomenological parametrization, where this is the ratio of the two gravitational potentials phi and psi. And if they are not the same, then quite generically, so if I took away my writing here, you would see that this is eta equal phi over psi. And so this is generically a sign of a modification of gravity. And this here is the what we normally call the mu parameter, which is the difference between the psi potential and the clustering components. And so if they don't fit, then either you have also modification of gravity, or you have some additional thing that clusters. So this is a mu beta plot.
Thank you.
That I relabeled to make it less cryptic. Okay, and so here, so to go back to this, here we have the number of generations, and you see that now cosmology also tells you that we are very, very precise to 3. So then these are the number of light degrees of freedom. I should put it like this. You could have very heavy additional degrees of freedom, but it is very consistent with 3, and it is not consistent anymore with 4 or 2. But of course, we know that we have at least 3 generations. Okay. So this was a bit the Planck and results part, and now, of course, there are many more results. Planck alone has actually published more than 100 papers, I think. So you can find a lot of the results there. But before I actually move to Euclid, I should also say that not everything fits perfectly. There are a few places where there are possibly cracks in the model. We are not yet sure. Maybe it's just problems in the observations. And so I think this is the one that worries or excites the community the most. Now, I told you that the expansion rate, as currently measured, is around 68 kilometers per second per megaparsec. But if you measure the expansion rate directly by looking at nearby objects, Then you find 74. And you see there is a significant, given the error bars, there is a significant difference. And you also see that there is a bit of a pattern possibly emerging, whereby you can ask me later to explain everything, but whereby local measurements tend to find higher values than measurements that look far away. So Planck doesn't measure the expansion rate directly. It observes the CMB and infers the expansion rate through a model. And so if these don't agree, then either some of the observations are wrong, or there is a problem in the model that's been used. Okay, and of course, having a problem in the model, that would be exciting because it would mean that we can discover something new. But the slightly disappointing part is that so far no simple models are easily able to explain this difference. So at the moment, this is a case where we have to wait for more data. Okay, so now where will we go in the future? So for Europe, one of the future experiments will be the next cosmology satellite, and that is Euclid. And so Euclid, in short, is a near-infrared and optical space telescope. So Planck was a microwave telescope. This is more or less an optical telescope, and that will observe nearly half the sky. The full sky is about 40,000 square degrees, and it will observe billions of sources and tens of millions of redshift. And also Euclid is actually a big collaboration. So you see, this is actually from 2013, the consortium meeting, and it's more than 1,000 members. This is a bit old. It's probably by now closer to 2,000 members. Planck was about 600, so this is 3 times Planck. Okay, so these are big collaborations. So here is the current status. So we are moving towards launch. Launch is supposed to be by now late-ish in 2022. You can also see that there are lots of acronyms. So we are about here. So more or less the Planck bits have been built and delivered, and now they are being put together, and the software pipeline is being put together. And then eventually it will launch, and then it will observe until about the end of the decade, but the data analysis will certainly also take longer, like for Planck. Okay, so here is actually a picture of the payload module integration in the actual flight model. So this is real Euclid. You always, with satellites, you don't only have one copy of it, you usually have about 2, 3, or 4 copies that are undergoing tests, that are being kept as spares, and so on. But so this is the actual flight model. And so here is the structure of Euclid. So what Euclid will do, it will take images in the visible, and so for the astronomers, here is the depth. It will measure the brightness in the near infrared, and it does low resolution spectroscopy in the near infrared. And you can see that it should measure about more than 1 billion objects so that we can measure their shapes, and about 30 million spectra. So this is for galaxy distribution, and this is for gravitational lensing. I will say a few more words about that, and all of that will then go together to obtain the best possible constraints. And so here is one of the main probes, and this is the galaxy distribution with the help of the spectra. And so you remember these peaks in the CMB. These peaks in the CMB, they are actually also imprinted on the galaxy distribution, but it's harder to see. And this peak in the CMB gives us a typical scale to use as a standard ruler, and it's the same in the galaxy distribution, and this is called baryonic acoustic oscillations, or BAO, and that we can use to measure the expansion of the universe over time. And in addition, galaxies fall into overdense regions, and that gives them velocities that shift them around in redshift. So what we observe are actually redshift, so by how much the light has been shifted, and that smears out the galaxy distribution in the radial direction. And these velocities tell us something about the depth of gravitational potential. And so a galaxy survey can measure these two things. And so that's one of the main goals for Euclid is to do that, one of the two main goals. And here is an example of how Euclid, you will measure the spectra to determine redshifts, and it will just smear out everything with the help of a grism in different directions, and then you have to reconstruct the spectra from this. So this is also an interesting statistical game. Okay, and here we put the Euclid Galaxy Survey a bit into context. So, okay, these are slides I borrowed from different people, this one from Will Percival. So here you see, as time progresses, how big the error is on this distance ruler, and you can see it's kind of an exponential decrease. And so the goal for Euclid will be, so now we are somewhere here, and for Euclid the goal will be somewhere down there. And here is the size of these surveys. So here is the area, Euclid 15,000 square degrees, and the number of objects. So you want to be in the top right corner. And so here you can see Euclid is fairly far in the top right corner. Okay, the second thing Euclid wants to do is gravitational lensing. So similar to what also affects the CMB. So when we observe the galaxies, we don't see them where they really are, but the light is deflected on the way. So that's indicated here by the structure. And so we see the galaxy displaced, but we also see their shapes distorted. And this distortion tells us something about the gravitational potentials on the way. And so this is a complementary measurement to the galaxy distribution. And Euclid will use 1.5 billion galaxies to measure this effect, to effectively measure the integrated gravitational potential over a sequence of redshift slices. And that will tell us a lot about what has been happening in the universe. And so to do that, you need pictures. And so here is an example of one of the 36 4K by 4K CCDs that Euclid will carry. And you can see the point spread function. So you need to really be careful. Do you also get cosmic ray hits and things like that? But effectively, you can think of Euclid as, I'll say that later actually, you can think of Euclid as being basically a Hubble Space Telescope-like observatory in space. And so here you can see also the increase in data quality over time for weak lensing. And so now we are about here at KITS and TESS, and the next generation will be Euclid and LSST. Okay, and so here is an example of the image quality that Euclid should have. So this is the Sloan Digital Sky Survey, the current, one of the current benchmark surveys. And you can see that Euclid will have the same, well, Euclid will have a much better picture quality, as I said, about Hubble Space Telescope level. And it will have about the similar picture quality at the redshift of 0.7 as SDSS has at the redshift of 0.1. Okay. And so Euclid, not only will it do great cosmology, but it actually will have also a gigantic legacy values for many other analyses. For example, it will see many dwarf galaxies where there are basically there are very few observed now. It will do amazing for strong lensing. It will like multiply the strong lensing data set by a factor 100 or more. It will observe very high redshift quasars. And here is an animation I borrowed from Jarle Brinkmann, if I can make it to work. Or maybe not, maybe I have to try to run it after. That is just to show how much the difference of the sky coverage is. Let me see if I can actually, here it goes. So this is the amount of Hubble quality imaging as a function of time. You can see Jarle made this picture in 2015, at which point Euclid was supposed to be launched in 2020. And so this is what will happen when Euclid launches in terms of Hubble quality imaging. And you can see that it's really a total game changer. So basically, Euclid will image nearly half the sky with a quality comparable to the Hubble Space Telescope. And so this will obviously have given the impact that the HST had, this will have a huge impact on astronomy. Of course, we are really interested in cosmology. And so here are the the goals here is, let's just focus on the neutrino mass scale, for example, and you can see that these numbers are below 0.06. And so Euclid and Planck hopefully will be able to detect the absolute neutrino mass scale. And here is the dark energy pressure in terms of the, well, let's pretend that this is W0 and WA. And so this is the Planck constraint. This is similar to the plot I showed before, just in a different parameter space. And you can see that this width here should shrink to 0.035, and this height, which is order 1 nearly, should shrink, oh no, sorry, this actually should shrink to 0.035. So this one should become a much, much, much smaller constraint. But of course, this is for the future. And that's why I prefer to give a bit more space to Planck, because for Planck, we actually can make the data plot. And for Euclid, we are still doing forecasts. Okay. So I think it's really time. I've been happily overrunning. So it's about time to stop. So to summarize, maybe the main point is that there is really a revolution going on and has been going on for 20 or nearly 30 years now in cosmology, where data has really been pouring in, and it will effectively go on. So, I mean, 100 years ago, we barely had a theory, and now we think we are pinpointing the precise description of the universe at the sub-percent level. But the problem is that, oops, that was not the way I wanted. The problem is that the model that we have, even though it fits the data very well, we have very precise constraints, it tells us that 95% of what is in the universe, we don't understand. So we have a model, but it doesn't really explain very much. And so the goal really is to change this and to try to understand what is the physical nature of these 95%, and how can we understand that they are there? Where are they coming from? How is it linked to the standard model of particle physics? Okay, and so we are really excited and looking forward to what we will learn with Euclid and other surveys. And so the very last thing I want to say is that the Planck data, and in the future also Euclid data, they are publicly available. And so if you want to try to analyze your own model, you can find the data and much of the associated software at this address here. Okay. Thank you.
Thank you very much, Martin. It was a very nice talk. So now we have time for questions. Let me see here. You can raise your hand to here. Okay, so Mauricio, you can start.
Thank you for your very pedagogical talk, Martin. I have two questions. One of them is just for you, ask you to compare the diameter of the Euclid mirror with that of Hubble Space Telescope, for instance, or Apache Point. Apache Point was 2.5 meters. Mm-hmm. And what about the Euclid and Hubble Space Telescope?
Yeah. Euclid is a 1.2 meter. Actually, for HST, someone maybe needs to quickly Google because I don't remember. Euclid is a 1.2 meter telescope, but it's quite difficult to compare ground-based and space-based telescopes because just because the atmosphere is getting in the way. So Euclid optimally, well, Euclid probably has a PSF of about 0.15 arc seconds. And I think on the ground, you're probably rather at 0.5, and the larger telescopes then, so Euclid is pretty much diffraction limited at the 1.2 meter. And the ground-based telescopes, they're usually atmosphere limited. Of course, with a bigger telescope, you get more light, so you can go deeper, faster.
Okay. And I would like to have some of your comments about this Hubble parameter tension. What do you think might be a possible way out or
Yeah,
comments. So.
I must say, I don't know. I should have maybe gone back differently. So my suspicion is always that it's a systematic, but the thing is, so in Planck, obviously, we have looked at this many, many times. This must be one of the most scrutinized numbers within the collaboration. But with my group, actually, we've also looked at, with my then PhD student, Wilmar Cardona, we've looked at this data set, and we try to introduce additional parameters that are so-called hyperparameters to turn off some of the data in case it's not compatible. And we didn't find anything suspicious either. Maybe the so-called distance anchor that you use to, because the way you measure this is over several steps. You have an initial distance measurement to a galaxy with Cepheids, pulsating stars, that gives you a luminosity distance then that you can use to go to further away galaxies with Cepheids, and that then you can use to go to galaxies with supernovae, and then you can use supernovae. And so the first step, this anchor to us seemed a bit a bit too much impact, but it was not enough to explain it. So there are maybe some more recent claims that say that there was a recent satellite Gaia that measures distances using proper motion, and that there was a problem in that satellite, even though that's not used here, but if you change that problem, then this number shifts down. Who knows? But so in principle, this seems very good. This seems very good. An interesting one is this, holy cow, this is a gravitational lens time delay measurement, and that was always supposed to give the best measurement of the expansion rate. And so the fact that this is here and consistent is actually quite a strong argument that that data point is true. But recently there have been other people who looked at the lenses and who changed the lens model, and then suddenly these error bars become much larger. So it's really difficult to say, see, there is another data point here that supports the Planck data point. Okay, so at this point, I think if there was a natural model, many people would say, well, it's probably real, and we have to change our cosmological model. But there has also been a lot of investigation. Can neutrino masses do it? Can a different dark energy do it? But all the models that can bring them into agreement, they're not very good. So I think at the moment the situation is really still very confused.
Okay, thank you.
Now, João Lobato.
Hello, Professor Kunz. I would like to thank you for the talk, and I would like to ask you two questions. First, how much model dependence you have on the conclusion of the flatness of the spatial? How much model dependent is the flatness of the universe, spatial universe conclusion? So,
well, it is always very, very model dependent. It's so model dependent, it's even hard to say how model dependent it is. But maybe what we can say is, if we believe in the cosmological principle that we are not living that the universe is isotropic and homogeneous, at least on average, then the most general metric is the Friedman, Lemaitre, Robertson, Walker class, and this is the one that was used here. So in that sense, if we believe in that, then this constraint is relatively good. However, if you allow for large-scale inhomogeneity, typically they have to be around us. Otherwise, we see a big anisotropy that we don't observe. Then you have a relatively big curvature close to us, and you can actually even remove the cosmological constant. So actually, Miguel, who is also on the call. He's an expert in these kind of models, so he actually knows much more than that about me than me. So so you can actually play quite a lot, but the question is a bit about naturalness. Also, then these large-scale inhomogeneities, they predict other things that that we don't observe, like high velocities. So in some sense, if you allow to be arbitrarily complicated, it's very hard to maintain the constraints from cosmology. But if you say, well, let's take the simplest model that is consistent with the data and with our basic assumptions like the cosmological principle, then this is a quite a precise constraint.
Okay, so the other question was about Project Euclid. So how much do you think that, or do you expect that Euclid data will be able to solve the Hubble constant tension? Do you think how could it contribute to solve this tension?
So the direct measurement may not even be quite so good, because Euclid starts to measure quite far out. I mean, at the basic level, Euclid takes a lot of pictures, so you can certainly use some of the analysis to place constraint. But Euclid itself will mostly measure distance scales at the redshift of 0.8 out to a redshift of 2. And so in that sense, Euclid is not the best instrument to test. On its own, it's not the best instrument to test that.
Okay.
So, yeah. There are other things that it will be very good, like another, maybe the second most worrying thing concerns the strength of gravitational lensing, where there is a bit of a discrepancy between the Planck inferred value and of the weak lensing observations, ground-based observation inferred value. But personally, I don't think that there is a significant discrepancy, but that one Euclid will clear up for sure, because there the statistical power of precisely that measurement is so strong. But for the expansion rate, I would actually have to think how to best use Euclid for that.
Just complementing, are these other local measurements also model independent?
They are more model independent, but I mean, there is always, so for example, these time delay measurements, they need a model of the lenses. And so if you don't know the model of the lens, then you cannot use them. These distance ladders, they are in principle relatively clean, in the sense that you but still, at every step you do make assumptions. So the way you do it is you need an initial distance to an object that you can then, so you use an initial distance to an object that has these variable stars, Cepheid, and then you need to use the Cepheid constraint. Basically, then you need to understand Cepheids. You need to understand your initial step. You need to understand Cepheids, and then you use that to go to supernovae. So you also need the supernovae. Okay, so there are also various model constraints at that level, but they are a bit less, they're possibly a bit less fundamental. But for example, for the Cepheids, those have been used for a very long time. So the point is, for Cepheids, the pulsation length is coupled to their intrinsic brightness, and so they give you a known standard candle. And originally it was used thinking that there was only one kind of Cepheids, but then it turned out that there are two different kinds of Cepheids. And so originally there was a mistake, because basically the distance was normalized using one kind of Cepheids, and then they used another kind that didn't actually have the same relation. So if there is another such problem in that data set, then you also have a problem there. So the problem, I mean, one of the problems in astronomy, and particularly cosmology, is that you always look at things from very far away. So you cannot really go and test.
But if I change the gravity model itself, the only measurement on this panel that would change would be the Planck result.
Yes, so if exactly, yeah, exactly. So if you change, so since this is, so here typically you would change the expansion rate because this is what we think of as a background thing. But for example, what you can also do is you could, again, like if we go to the model with a local inhomogeneity, then of course, this measurement here would mostly measure the local value, which then would be different from the distance value because locally we may be in an underdense region, so we have a different expansion rate naturally than objects that are far away. Or if your theory of gravity changes the expansion rate, you can bring them into agreement. The problem is that you basically need phantom dark energy. You need a pressure that is more negative than -1. And so that is normally not seen as so very attractive, but who knows? So it's, for that reason, it's all, I mean, yeah, it's, you can find models that get them into agreement, but, and so, yeah, so I think if something happens at these distances, Euclid may be able to pin down the expansion rate here much better. So the kind of phantom dark energy model that you need, Euclid probably should pin it down. Euclid should also be able to provide better constraints on the way the curvature changes as a function of redshift by comparing expansion rate and distance measurements. So in that sense, Euclid should tell us more things, but and we will certainly learn it. I think in 10 years we certainly have made progress on it. So but in which way it will go, I wouldn't dare to predict right now.
Okay, thank you.
Okay, I have a question. It's a bit more general question about this. There was an announcement by the BICEP collaboration, I think 2014, about the imprint of the inflation in the CMB.
Yeah.
And so I would like to ask you two questions. One of physics. Is it in your next projects will address this question, the Euclid satellite, and yeah, especially the Euclid satellite. And another question is that in these big collaborations, I also work in a big collaboration. We have pressure to produce, headlines and very nice results, but how you in your collaboration, how you deal with the pressure of produce very nice results and publish quickly, and at the same time maintain the scientific integrity, how this works?
Yeah, so okay, which part should I, let me first talk about the sociological question.
Okay.
So in Planck, there was maybe a bit less pressure because the data was getting public, but it is very hard to analyze. So basically the Planck collaboration was more or less the only group that could really authoritatively analyze the data. So there was not a huge, and ESA also gave us a bit more time. So there was not a lot of pressure to publish quickly. And the main movers, the most important people in the collaboration, they were really very careful that we wanted to have, and that's not me at all, but as a collaboration, we really wanted to have correct and good results rather than speculative results. Actually, there was maybe even more a drive towards staying with the not to overclaim, so to be rather more conservative. And so generally within the Planck collaboration, there was really not a big pressure in that direction. So that was actually quite good. Also because for Planck, all the paper releases were all coordinated. There were only collaboration papers. There were no subgroup papers. So all of this. In Euclid, it will be a bit a more mixed model. So there we will have to see if some subgroup finds some interesting result, how that will play out. Because Euclid will have both collaboration papers and papers by subgroups that others can then join. But there is a fairly strict internal refereeing process. And I think that also there will be a strong constraint to be reliable, not to claim anything too early. Of course, it always also depends on what you discover. Now with BICEP, to get to that question, with BICEP, it was so that they were working actually with Planck at the time. And then they saw this signal in this B-mode polarization that I didn't really mention, that was exactly consistent with the expected signal. And then they decoupled from Planck. The problem was that the information they had from Planck was not complete. So they knew that Planck knew that in the area they were observing, the intensity of the foregrounds was relatively small. But what they hadn't known was that Planck had seen that the polarization of the foregrounds was quite strong. And so even though the intensity was not so high, the impact on polarization was higher than expected. And so then they were a relatively small group. And so then they decided to go ahead and publish it, because this would have been a Nobel Prize result. Okay. And so then the experts within Planck very quickly realized that this was probably foregrounds. But and here actually this constraint, when you see BK15 here, so the red and the blue that are much stronger than the gray, these actually now include the BICEP data, but using Planck to foreground clean the BICEP data. Okay. So the strongest constraint here is the combination of Planck and BICEP. Now Euclid, I don't think Euclid will say a lot about primordial gravitational waves, because I'm not it would be very hard for Euclid to observe them. What Euclid can say more about is the tilt, because that is something about the clustering, and about another thing that I haven't discussed at all, non-Gaussianity. So is this initial distribution, is it really a Gaussian random field or not? And that tells us things about, let's say, if it's really an inflation field, an inflaton field, it would tell us about couplings in the inflaton field and so on. But Euclid will, I don't think Euclid will tell us a lot about the primordial gravitational waves. There, the probably best, so there are some ground-based, so the CMB is kind of probably the best way to see it, apart from actual gravitational wave detectors, but even they have problems because it's so low. The CMB is nearly the best, because the gravitational waves, they perturb the polarization and they create this, or rather their presence creates this B-mode polarization, and on large scales, nearly nothing else creates B-mode polarization. On small scales, also gravitational lensing does. And the problem is large scales are hard to observe from the ground. So that's best for satellites. But the Japanese are building a future satellite, Lightbird, that is expected to be launched in about 2028, 2030. And that one will should actually go to about 10 to the minus 3 in this primordial, in this tensor to scalar ratio, which is what this axis here really is. So I think there we have to wait for that satellite, or possibly the ground-based CMB experiments if they manage to de-lens, to remove the lensing part. But yeah.
Okay, thank you. There are other questions? If not, then I would thank very much Martin for this very nice talk. And maybe if you want to say something else, just to finish up.
Well, generally, I would like to thank you again. And maybe actually one point I would like to make, which I think became a bit clear, is that the best constraints in cosmology, also because of the model dependence, they usually don't come from a single experiment or a single observable. So it's really putting these observables together is really what gives you the best power and allows you to cross-check your models. And I think this is also a very nice aspect, also in terms of collaborations between different groups. And so this is one of the things that works actually quite well in cosmology. So beyond that, well, thank you very much. It was really a pleasure to give this seminar. As I said, it was certainly easier to give it across Zoom, but it's a lot less pleasurable to have to do it across the Zoom link.
Yeah, we hope next time you have a caipirinha after the
exactly.
talk.
I'm looking forward to that.
Okay. Bye-bye. Thank you, everyone.
Bye.
Next week. Bye-bye.